Now, this last lesson, the third lesson, this is the 5th unit, is on absolute extrema, or optimization, okay? And we remember from 2 units ago how we could find relative extrema of functions. I would take the derivative, and I'd find out when the derivative was a positive or negative, because I would tell me when my function was increasing or decreasing. To figure out when something's positive or negative, we start by setting it equal to 0, or we see when it's undefined. We don't have to worry about undefined in this situation. We factor to solve, we get 2 solutions for when our derivative is 0. We know that the signs are going to be the same in between our intervals. If something is positive, everything's going to be positive in this interval, or if something's negative, everything's going to be negative. We plug in test points into our derivative, the simplified derivative, which is this guy, because it's a little bit quicker to work with. I plug in 3, positive times a positive is positive. I plug in 1, positive times a negative, negative. I plug in -1, negative times a negative is a positive, okay? This is telling me that I have a function, f, my original function here, this x cubed function. It's going to increase until we get to 0, then it's going to decrease until we get to 2, then it's going to increase after there. Well, that means 0 is a relative max, 2 is a relative min, right? And we can kind of sketch that, and I could even plug in points and get 0, 5 as what we're going to increase to. I could plug in 2 and find that value to what we decrease, and we can say, okay, that's f. That's great. Well, absolute extrema are the overall maximum or minimum values of a function. For example, for this graph right here, we have an absolute max. It is also the location of a relative max. Here, we have an absolute min, which is also the location of a relative min. Okay? So the biggest function value and the smallest function value. However, if we look at something like this, we have a relative max and a relative min. However, these are not absolute maxes and absolute mins, because the function continues to go up from here, it continues to go down from there. So we have no absolute maxes or mins. And lots of functions will not have, horizontal asymptotes at 0, like this guy, or be kind of stuck here. And so a lot of functions won't have an absolute max or an absolute min. If you look at a squared function, we know it has a min or a max, one or the other, but not both. X squared would have a min. Something like a negative x squared would have a max, but it would not have an absolute min. Okay, does that make sense? Well, because of this reason, the fact that not every function has an absolute max or min, typically you'll be asked to find an absolute max or a min given an interval. Okay, so sketch down this function to look at a closed interval, and we will find the maxes and mins at a closed interval. So the question that you will see a lot is, what is the absolute max or min inside the interval from -2 to 3? Notice they are closed brackets, so we are including -2 and 3. Okay? Well, you would look at just this portion of the function. And you would find the maximum and minimum value of that portion. And you can see that right here, that would definitely be the absolute max. And right here at 2, that would definitely be the absolute min. Both of these are locations of relative extrema. This is a relative max and this is a relative min. But watch what happens if I change the question to be from, say, 0 to 3. And I look here to here. This relative min will also be my absolute min, just like it was for the other interval. However, the max is not at a location of a relative max. Where is the max in this situation? At 0, right here. Since we are including 0, we have this point 0, whatever it is. That point, which is an end point, is our max. What is this telling us? If you're trying to find an absolute max or min on an interval, you must check locations of your relative maxes and mins, but you also have to compare those relative maxes and mins to your endpoints. This is called the candidates test. Given an interval, a closed interval, absolute maxes and mins occur at either the locations of the relative max and mins or the endpoints. And that's kind of what's new. Now, let's do an example. Find the absolute extrema of x cubed minus 3x squared plus 5 between 1 and 3. Okay, there's a couple ways that we can kind of go about this to ensure that you have the correct location of your max or your min. Okay. Now, we can start by finding our critical points. So finding our relative extrema. Same as our first one. Now, 0 is outside of my interval. So I don't care. Okay. Now, a couple things we can do. I can go straight to the candidates test, and I can compare the y value at 2 to the y values at 1 and 3. And then boom, I'll have all 3 candidates. I know that one of them will be the absolute max and one of them will be the absolute min. Sometimes that's the quickest thing to do. So I can compare f of 1, which is an endpoint, to f of 2, which is either a max or min. I don't know, but really I know it's a possible candidate because it's possibly a location of a relative extrema, and f of 3. And I plug those values in here, to my original function. Compare candidates. And I get 1 minus 3 plus 5, so that's negative 2 plus 5, that's 3. I get 8 minus 12 plus 5. 8 minus 12 is negative 4, plus 5 is 1. And 3, I get 27 minus 27 plus 5. 5. I've exhausted all of our candidates. Since I've done that, I can easily say and comfortably and confidently say that x equals 2 is the location of our absolute min. X equals 3 is the location of our absolute max. So those are the locations. You might also be asked, find the max values of the function. If they ask you for the maximum or the minimum values, the answers are the y values. So you would say that 1 is your minimum value, 5 is your maximum value for this function on this interval. Okay, location of it and the point. Okay, now we also could have come to this conclusion, at least for 2, by looking at the signs of f prime around 0 and 2. We already did it up here, that was positive, negative, positive. Well, you know that if the derivative is negative everywhere between 0 and 2, it's definitely negative between 1 and 2. So if you're going down from 1 to 2 and then up from 2 on, you definitely know that 2 is going to be the location of your absolute min. Then you could have just checked the locations of your other endpoints for the absolute max. So that is a possibility. You could also just look at what we've looked at in the past, the signs of f prime, for you to know that if you're starting at 1 and going to 3, you're decreasing until you get to 2, you're increasing after 2, this is definitely the location of the absolute min. We comfortable with that? Okay, good. Not necessary. However, sometimes you won't be given an interval. If you are not given an interval, you could use the signs of f prime. And you know that if you have a very set interval from one location to another location, if you are going positive to negative, this is definitely going to be the location of your max, because f is increasing and then decreasing. You know, if you have a very set interval, and in that set interval you're going from negatives to positives, you know this is definitely going to be your min, and it's going to be your absolute max and your absolute min. Okay? So sometimes you can check that, and that will give you confirmation that, boom, not only is this the maximum, a relative maximum, it also is the absolute maximum, or this is an absolute minimum for your interval. Okay, a lot of times we will start at like 0 when we're talking about time. And you know if you're going down then back up, or here, up then back down, boom, you're good. Okay, so that's called the candidates test. You also have that first derivative test. Some other questions that could be asked of you that really are just absolute max or min questions. We have a particle with a position. You're asked, when is the particle furthest to the left? Okay. The question furthest to the left would be the absolute min of your position, right? If you think about position, if you have negative values, you're moving to the left. If you have positive values, you're moving to the right. We're figuring out when are we the furthest left, whether in the negatives or in the positives. Okay. Now, for anything, when you're trying to find a max or a min, it all comes back to a simple concept: taking a derivative and setting it equal to 0. Okay? Whenever you're involving any type of extrema, whether it's relative or absolute, just make sure we know that for all of these, take the derivative and set it equal to 0. Whatever you're trying to find the max or min of, start with that, right? And then we can do the analysis from there. So I want to find when this is a min. I'll take the derivative of this and see when it's a 0. Now we should also check to see when it's undefined. We have locations where that could be an absolute max and that derivative is undefined. However, for most of our problems, we won't have to worry about this because we don't have a denominator. If we did have a denominator, we would have to check. Okay. I factor to solve. I get two possible solutions, 0 and 1. I can either look at the signs of my derivative, or I could go straight to my candidates test and look at the positions at 0, 1, and 2. 0 being a possible relative min or max, as well as being an endpoint. 1 being a possible relative min or max. 2 being an endpoint, a possible min or max. Okay, so why don't we just do that if it's easy to do? It's pretty easy to plug in 0, 1, and 2 into this, so I'm going to do it. This is candidates. I get 0, 2. I get 1, which is 2 minus 3. So that's negative 1 plus 2. That's 1. And 2, I have 16 minus 12, which is 4, plus 2 is 6. So it turns out 1 is my absolute min. So when it will be when the particle is farthest left. Okay. Could we have checked another way? Yeah, we could probably have done the first derivative test and just kind of looked at, well, 0 is where I start, 2 is where I finish. I have 1 in between those hard set values. I can look at 0.5. That'd be a positive times a negative. It's a negative. I can look at 1.5. This would be a positive times a positive. That's a positive. So there you go. You can see that I have to go down from 0 to get to 1. I have to go up from 1 to get to 2. This is definitely going to be the absolute min. Okay? Two different ways to do it, either using your candidates or analyzing your first derivative. Okay? We could do the same question as above, but now the question is, when is the particle moving fastest to the left? Let's make it fastest to the right. Yeah. What am I trying to find if I'm seeing when something is moving the fastest to the right. The max of what? The derivative, what is the derivative of what? Max derivative of what? So we're finding the max velocity. Exactly. That's what I'm looking at. We can start by just writing down what we're trying to find. I'm trying to find the max velocity. How do I find the max velocity? Do I plug in values into 6t squared minus 6t? No. How do I find the max of something? Take the derivative, set it equal to 0, look at your candidates, or examine the signs of your derivative. Okay? That's how you find the max. Derivative set equal to 0. That's how we're going to find the max of something. Okay? Want to find the max velocity? Take the derivative of v of t. V of t we have up here. It was x prime of t. V prime of t equals 0. That will be 12t minus 6 equals 0. Giving me a candidate, t equals 1/2. You guys discover when we have the particle that's moving the fastest and what is the velocity. So how fast? Go. What do we get?
Right. Two, but then I realized I just
Right, so it would be 1/2. You just add 6 divided by 12.
Yeah.
So you checked 1/2.
I got negative something, but I forget that was enough.
Right, so you checked 0 and 2, and you got that. Okay.
Oh yeah, that's right. Never mind.
Okay, good. Good. Is our max at 1/2? Is it? Good. That's correct. So our max is not at 1/2, right? How can I confirm that? Well, if I wanted to, I could have looked at my interval between 0 and 2. I plugged in something like 1/4. I know this is going to be negative, and then this is going to be a positive. So this is a min. So that's not going to be my max. The max is either going to be at 0 or at 2. We can't just assume it's at 2 because we could actually start from a higher location and go down more than how much we come back up. So make sure we're not just assuming because we're going plus here and your function's increasing that we did not start at a higher point. So really our comparison is between 0 and 2. Now all you could have done as well is just compare your candidates using the candidates test. Check at your different locations. Your velocity at 0 ends up being at 0. Your velocity at 1/2 we know is just out. It's 6 times 1/4, which is 3/2, and then minus 3. So 3/2 minus 6/2 is negative 3/2. And then we check 2. 2 squared is 4 times 6 is 24 minus 12 is 12. Aha! This is when I'm moving fastest to the right at that interval. when t equals 2 and at a speed of 12, whatever we're talking about, units per whatever. Questions? Is this cool? Okay, so that's kind of the first part of things. Now, we also could have some weird questions like with ease. When do we have an absolute max for this? Now, this is a little trickier. I'm just going to show you how to do it. I take the derivative of this. I have to use the product rule. Derivative of the first times the second plus the derivative of the second. Derivative of e to the power is e to the power times the derivative of the power times the first. Okay. I'm going to set that equal to 0. How to solve something set equal to 0 with e's in it? Factor out the e. The negative and the negative will cancel. This is always positive. No matter what the power is, e to any power is always positive. So I really need to figure out when just the middle part equals 0. That's when x squared is equal to 1/2. That's when x equals plus or minus 1/2, root 1/2. Now, if I tried to do the candidates test, do I want to plug in root 1/2 and compare it to negative root 1/2? And do I even have a closed interval? No, I don't. So I actually need to go about this another way. I need to start by kind of seeing what's going on around these numbers. So I'm going to do my first derivative test, which is just plotting down our values and examining the signs of my first derivative. Okay. Now, what's great is that I can use a test point like 0. Now, again, this is always positive, so I'm just looking at this term, since it's always going to be a positive times something. If I plug in 0 in here, I get -1, so that's a negative, which means this is a negative. Okay. If I plug in something over here like -2 or -5 or whatever, well, again, this will be positive no matter what. So it would be -1 plus 2 times -5 squared. Well, -5 squared times 2 is definitely going to be bigger than -1. So this becomes a positive. And then I look at something like 4 or 5, and I plug in that, and that's positive. I plug in 5, definitely positive as well. Okay. Well, where do we have an absolute max for this one? There's actually 2 possible candidates. There's one candidate, and then there's also another one that's not really a candidate. You can tell me one candidate, Mr. Quigley.
I guess negative root, like, yeah, negative.
Negative root 1/2, right? Possible candidate, right? Because we're going from increasing to decreasing. What is another possibility? Right, infinity. Maybe there is no absolute max because this is plus, so this is saying that I'm increasing. So if I'm increasing, then decreasing, then increasing, maybe there's no absolute max. What are we going to have to do? We're going to have to see what the limit as x approaches infinity of this guy is. And if it is infinity, well, then there's no absolute max. If it's another value, we're going to have to compare it to our value at negative root 1/2. What is this limit? Let me rewrite it for you. As x approaches infinity, the numerator is growing, but the denominator is growing much, much faster than the numerator. What will this approach? Thank you. This is approaching 0. If we looked at the other direction, as x approaches negative infinity, since I'd be squaring it, as we're going towards negative infinity, we're approaching 0. So it turns out this function looks like this. Yoink, yoink, yoink. Where we are going to be increasing, but we are going to be increasing just infinitely slowly, approaching 0. That confirms that this, as long as that's a positive value, if I plug in negative root of half, I'd get a positive value, because negative times a negative is a positive. E to any power is a positive. Since this is a positive value, there's my absolute max. Isn't that kind of crazy? It's a little tricky. Okay. There are other types of optimization problems. Like building a house that has a certain amount of space with the least amount of material, or finding a route that's minimizing the distance to travel. The key is you're going to just have two equations. One you will use to plug into the other one you're going to derive. Okay? Here's a simple example. Find the two positive, we'll call integers, x and y, where the product is 192, and the sum of x plus 3y is a minimum value. Now you can go ahead and try to exhaust this problem by finding all of the integers that multiply together to get 192, and then to plug them all into x plus 3y to get your answer. But calculus helps us figure out this better. The sum of x plus 3y is what we're trying to minimize. How are you going to minimize? You're going to take this derivative and set it equal to 0. But don't do it yet. Because we have another piece of information. This is kind of like my supporting equation, where I actually can figure out what one variable is in terms of another. X is 192 divided by y. And I actually can take that and plug it into this to get that. Is that going to help me? Yes, tremendously. I'm going to take the derivative of this. Now I'm going to rewrite this as y to the negative first. And I'm just going to take the derivative of this with respect to y. Whatever variable I have, I'm going to say this is negative 192 over y squared plus 3. This is set equal to 0. We will solve this, subtract 3 times y squared. What's 192 divided by 3? Is it? 64. Oh my goodness, it's almost too simple. And then the square root of 64 gives me plus or minus 8. We'll typically use just the positive values. Well, if we have x times y is 192 and x is 8, y is 192 divided by 8. 192 divided by 8 is what? What's 192 divided by 8?
The answer is 24.
The answer is 24. Thank you. Okay, so there's a couple more examples of this type of problem that you need to watch and then do the quiz to prepare yourself for the test. Examples are, a gardener wants to make a rectangular enclosure using a wall of a barn as one side and 120 meters of fencing for the other three sides. Find the dimensions that give the greatest area. Another one would be like, yeah, like that one and a couple others. They're going to be on the websites. And again, make sure you do that quiz, which is online. I don't have copies made of that third quiz, to make sure you know what you're doing for this lesson. Make sure you redo the other two quizzes. Test on Monday. You got the weekend to study. Email me with questions. Come in the morning on Monday with questions, okay? Thank you. You too. Thank you. Okay, let's do the Gardner problem. So we have a rectangular enclosure. You have a wall of a barn. So here is our barn. We're looking from the roof here, bird's eye view. And then we have a rectangular enclosure here. We'll say that we have a side X. So this is rectangular, that's X, and this is a Y. They're not the same, they might be the same. We have 120 meters of fencing for these three sides. Now we want to get the greatest area, so we want to max my area, which is going to be my length times my width. Okay, so this is the one that I'm going to take the derivative of. This is my optimizing equation. And I need kind of like a supporting equation. The supporting equation comes from the 120 meters of fencing that is going to be for the other three sides. So that means the perimeter of this fencing is 120. 2x plus y is 120. I will then solve for one in terms of the other. I think it's going to be nice if I solve for y. I'll get 120 minus 2x, plug that in, and once I've eliminated that, it's actually going to be easier for me to take the derivative, set it equal to 0 to find the max. And then we'll compare our candidates. So this is 120x minus 2x squared. Take the derivative of that. I get 120 minus 4x. I get x equals 30. Now, this is my only candidate. I can kind of confirm that this is going to be a max. I'm going to be looking at starting when x is 0 and then going off forever. If I plugged in something like 10, this is positive. If I plugged in something like 40, this would end up being a negative. So definitely having a max here. So this candidate is my only candidate because of this first derivative test. All right, so that's 30. That means that y has to be 60. Okay, so those are my dimensions. This is 30, and this is 60. And now give me my greatest possible area with 120 meters of fencing that I can use. Next question, different type of question using logs. So a changing triangle is created by using the vertices 2, 0, and 5, 0. So here's 2, 0. Here's 5, 0. And a vertex given by the points on the function log of x squared minus 1/2 x plus 3, where x is on the interval from 1 to 6. So I have some function. I don't know what it looks like, but I have like another point that could be like anywhere. And, it might even be here. It might be a negative, okay? So the question is, when are we going to have the largest area of this triangle? No, the question isn't even stated. I'll say, when does, or for what point on f of x will the area of the triangle be the largest? Well, let's think about the area of a triangle. It's 1/2 my base times my height, 1/2 my length times my width, my horizontal times my vertical in this situation. Well, my vertical is actually this, and my horizontal is this. So it's actually a situation where I want to maximize 1/2. My horizontal is always going to be 3, and my vertical is y. Well, I could also just plug that in for y, or I can just think about, I need to figure out when y is the greatest or the least on this interval from 1 to 6. You know, it could be over here, it could be over here, like just when are we the highest or the lowest, because the area of a triangle is just 1/2 my base times my height. So I could just maximize or minimize this, or maximize, minimize this with that plugged in, okay? Either way works. Let's just go and just look at this and find the max or the min of that. So to find the max or min, I'm going to take the derivative and set it equal to 0. It'll give me some candidates. I'll compare some candidates with my endpoints as well, my intervals from 1 to 6. So let's do that. So my derivative of log of x squared is 1 over x squared times 2x. Derivative of 1/2 of x is 1/2. That's my derivative. Set it equal to 0. See when it's undefined. The x's cancel. And I have 1 over x minus 1/2 equals 0. Don't forget, we're also going to see when it's undefined. In this case, we can be undefined. So we are undefined when x is 0. And what has to be here? Well, 1 over 2 minus 1 over 2 is 0, so 2. Well, thankfully, my interval's from 1 to 6, so I do not have to include 0. So I have a possible candidate 2. Now we can either work our first derivative and the signs of my first derivative on my closed interval from 1 to 6, and I could check out 2 by looking at this derivative. Well, if I plugged in, you know, like 1/2, 1 divided by 1/2 is 2, 2 minus 1/2 is positive. If I check something after 2, like 3, 1/3 minus 1/2, that's going to be a negative. So if I start at 1, we are going to be increasing until I get to 2, and then decreasing from there. So I definitely have a max. And these are possible locations of our min. So actually, I'm actually going to have to do the candidates test, because if I had a negative value, like all the way down here somewhere, maybe that negative value would produce a larger area than my positive value. So let's go ahead and check our candidates. So I need to check f of 1, f of 2, and f of 6. And it might be difficult to do, but let's see. I have the log of 1 minus 1/2 times 1 plus 3. Log of 1 is 0, so negative 1/2 plus 3 is 5/2, 2.5. Okay, so let's check 2. I know it's going to be bigger than 5/2. So I plug in 2, I get the log of 4 minus 1 plus 3. So this is the log of 4 plus 2. And then I check 6. I have the log of 36 minus 3 plus 3. So I really have to compare log of 4 plus 2, log of 36. What's going to give me the biggest? Okay, well, this is good. This is really good, actually, because I don't know how to compare these two. You know, it's like I'm not sure which one's bigger, and I don't know how to compare them, all three of them. But there is something that I do know, is that they're all positive. That's positive. I know the log of 4 is positive. I know the log of 36 is positive. The only time that we have negative log values if we're talking about something that is a fraction, like e to the negative first, something less than 1. We are all greater than 1 here, so these are all positive values. So really, going back to that first derivative test, we know that we are going to be increasing until 2, then decreasing after 2 to 6. This number here is going to have to be the maximum y value. Now, since this is the maximum y value, that would be the point. If I wanted to find the area, I would have to do the 1/2 times the 3 times that y value. So 3/2 times log of 4 plus 2. And that would give me the answer for my y value. I can double check just because I can. There's 5/2. This is log of 4 plus 2. That's bigger. Log of 36. Is bigger. What did I do wrong? I might have done something wrong. Let's think about this. 6 divided by 2 is 3. 3 plus 3, negative 3 plus 3 is 0. So this is the log of 36. Did I take the derivative correctly? 1 over x squared times 2x minus 1/2 equals 0 undefined. I got 0 and 2. Oh my goodness, Mr. Messner, you screwed up. This is a 2 minus 1/2. X should be 4, not 2. This should be 4. If I plugged in 4, I'd get the log of 16. And then minus 2 plus 3. So that'd be plus 1. Oh, watch this. Log of 16 plus 1 is going to be bigger than the log of 36. Gosh. Log of 16 plus 1. That's what happens when you rush, folks. Don't rush. There is that maximum value. That is definitely the maximum value. I'm very confident in that. And look at that. If you do make a mistake and you're guaranteeing that an answer is the answer, and then you look back and you say, well, nope, something must have happened. And here's the problem. I forgot about this 2. This 2's up here. Shoot. Don't rush. Step by step. So there you go. That's another optimization problem. All right. Thank you.